Okay, welcome to your first video. This is a video supplement, chapters 1 and 2, and the title of this module is called Environmental Problem, Sustainability and Science. So, since this is your first video, let me make it clear that these videos are not meant to replace your reading. They are a supplement, hence the word supplement, to the reading, as are the slides. So these are three different sources of information. They should not be, one should not be used in skipping the other. And the process should be, as you noticed from your online information, you should be reading the chapter while reviewing, if you will, the worksheet and the quiz so that you know what's being emphasized as you go through that chapter. So have those reviewed as you read the chapter, and then you watch the video. Okay, and these three sources of information, the PowerPoint slides, the video, and the chapter, rounds out the entire information. They're not to be one replacing the other, skipping one to do the other. They're to be all included in your learning process. So, the videos typically are going to supplement the information that's typically not covered much in your reading, and the slides are meant to be more of an outline with a little bit of additional supplement. So let's jump right in here and talk about natural capital. This is something that's introduced in your book. And when we talk about natural capital, what we really mean are natural resources plus natural services. And you should have got an idea of what these are from your reading. Natural resources, I think most people know, are these materials that are present in our earth, in our environment, that we can use to benefit us or for some need. Okay? And they're broken down into both renewable and non-renewable, as you know from your reading. The natural services, if you will, these are processes in nature such as purification of air and water and renewal of topsoil. So the actual processes of how the natural resources, if you will, are kind of purified and maintained. So when you talk about natural resources, some of the resources you should have come across and things you think about are things like fossil fuels, wood, air, water, stuff like this. Some of these are renewable and some are non-renewable. If it's renewable, it just basically means that it's replaced. Once you use it up, it is replaced. A non-renewable resource is something that takes too long basically to be replaced. When you think about fossil fuels, I mean, ultimately they will be replaced, but it takes millions of years to form them, so they're considered a non-renewable resource. There are some things that are virtually like perpetual resources. We call them renewable, like solar, sunlight, solar energy. We consider that renewable, but it is virtually perpetual because it's for all practical purposes, within our lifespan, it's not going to need to be, if you will, renewed. It's a continual source. You can have renewable resources that you're using at a rate that's faster than they're being renewed, and that's what leads to problems like degradation or capital degradation. So if you use that resource faster than it gets degradation, then it gets renewed, then you're degrading that capital. And that's one of the key important things here, is that things like some of our metals in our environment that we use a lot of, these are set stocks, if you will. They are exhaustible. They can be managed as a renewable resource if we recycle all these materials, all these metals that are used in our electronic components and a lot of our appliances, things like that. But in many cases, we're using them and they're going into the market and not being recycled at a rate that keeps up with what the environment's able to renew. One example is phosphorus. Because we use phosphorus a lot in our agricultural practices, we are using it at a rate in which we are depleting those stocks, and the recycling process is too slow to keep up with that. So that is a major concern we're dealing with. Those are the only two major things I want to point out from your Chapter 1 reading. Remember, this module includes 2 chapters. All the other modules basically are going to be 1 chapter. And the rest of that chapter is really well laid out and well explained, so I don't think I have to really go into much. So here we are into Chapter 2. I want to point out the scientific process. And your book has a couple really good figures here, and there are 2.2 and 2.3. I think I mentioned that in the slides. You should look at closely, showing you the scientific process. I mentioned in the slides, it's mentioned in your reading, that this process involves things like observations and hypotheses, and then testing these things with experimentation, modifying your hypotheses, maybe coming up with laws and theories, and continually testing these things. I gave you a definition for law and definition of theory in your slides, so pay attention to that, because the one in your book is a little bit less detailed and maybe not as good, in my opinion. So I've tried to enhance what you've got from your book. I do want to say that the scientific process is much more than just the scientific method, if you will, which is what you all know as, observation, test. It's the whole process that separates out science from other disciplines, and that is the peer review process. If you go to publish, like if I do research with my students, we go to publish that data, we're going to have to actually have that work reviewed by renowned scientists from all over the world before that paper can be accepted for publication. And it's a very objective process. Did he do the necessary experiments? Is his data appropriate? Are his methods sound? And can this be reproduced? That's one of the keys in this field, that the research has to be reproducible. Well, if you submit a poem for publication, obviously that's not going to be reproducible, and that is much more subjective. It's not based on any sort of data. That is what sets science apart. So that is all part of the scientific process. And it's, if you will, it's that peer review process that is key to science. And that's how we come to a conclusion, if you will, not a final conclusion, but a consensus that leads us to a prevailing theory. And we say, okay, this is what the majority of scientists believe, so this is what we're going to teach to our general public. And as things might change and get modified, we update that. And we've had plenty of scientific revolutions in our history where, we had data that supported certain things, and this is the way we taught it, and this is the way we believed it to be true, until additional data came along and we modified that and revisited it. We don't typically throw things out. We simply revisit, modify. And so a theory is a very moldable concept that changes as you get additional data. As far as atomic structure, you all probably were exposed to some sort of atomic structure in high school. And a very basic structure, of course, then, is you have the atom with the nucleus. And in the nucleus, you have your protons. Your book uses P to signify that. Some people use P plus because they are positively charged. There's also neutrons in the nucleus, which have no charge. And surrounding the nucleus, you have electrons, which are given an E with it, sometimes a negative also. And one thing you should have realized maybe at some point in your learning is that you might have learned about the law of charges. And that's the one that says opposite charges attract and like charges repel. Well, here you have a nucleus packed with a bunch of like charges, right? Because neutrons are not charged at all. It's a bunch of protons packed into a very small space. So you might wonder why they don't repel each other, because that's what the law of charges tells. Well, it turns out they actually do. And that's going to be the basis for radioactive decay, which is talked about in your chapter here, and I'm going to talk about in a second. That some nuclei, some of these nuclei in atoms of elements are unstable. Not all of them. And there's reasons why some are and some are not. But that is what radioactive decay is, that unstable nucleus as a result of these repulsive charges. So some of the other things in atomic structure you should be reading about, getting familiar with, is what elements are and isotopes, molecules. There's something called the mass number. That is the number of protons plus neutrons. So if you add those two together, that is your mass number. And sometimes we notate this like this. Here's the symbol, so that's carbon. Up here is going to be your down here is going to be your number of protons. That's your atomic number. And up here is your mass number, the top number. So you might have something like this. That means it's got 6 protons plus 6 neutrons, because that's where the total number 12. And these two right here are inseparable. They go together. If I say carbon, I mean 6 protons. If I say 6 protons, I mean carbon. There's no exceptions to that. The number of neutrons can change. That's what isotopes are. I need you to know what isotopes are. Also, you can have ions. Ions are atoms that gain or lose electrons. So the number of electrons can change. Number of neutrons can change for carbon. But if it is carbon, it's always going to have 6 protons. And that's really important that you realize that. And if we have ions, we typically should put a charge in the upper right-hand corner. So that would be the chloride anion, negatively charged. And this would be the sodium cation, positively charged. So your book also talks about ions, and a couple important things with that will come out later is acidity and pH. Now that'll become important later. We talk about acid rain and stuff like that. But one thing you are looking at with acidity is really a combination of these two ions. And some ions can have more than one atom. So this has 2 atoms, oxygen and a hydrogen. And this is a hydrogen ion. And that's really what acidity is, a measure of this. And if you have a strong acid, or I should say something that's very acidic, it has a bunch of this right here. It's all really go into right now, and I'm not going to ask much more of that. In the pH scale, your book talks about this, or read this, but we'll come talk about this when we deal with acid rain. So there's a couple other things that are pointed out in your textbook that I need you to be familiar with. Okay, and then I want to mention the periodic table. And I've given you a copy of a periodic table here, and I think it occurs somewhere else also. I want to point out that all of these ones that are kind of like a bone colored, if you will, these are metals. The blue ones are nonmetals. And the green ones are metalloids. And some people call them semi-metals. And you think about metals, they have characteristics of conducting electricity and heat. They're malleable and ductile. That means we can put them in wires and make them into sheets. Metalloids are somewhat in between metals and nonmetals don't have the characteristics I just talked about. They don't conduct electricity or heat. So some of these elements will become very familiar to you. As we talk about solar cells, we'll talk about silicon. When we talk about nuclear fission, we'll talk about uranium. Okay, so a lot of these are important, and you'll see they're color-coded here. And what you notice, the atomic number is the number up above. That's the number of protons. The mass number does not appear on the periodic table, does not appear on any periodic table. Many periodic tables have a number down below here, which is your atomic mass, which is the average mass of all the atoms of that element. And I'm not going to go into that right here. And there's no need for you to worry about that right now. This periodic table I picked was very simple just to get you exposed to them. So once again, you'll notice that most of the elements are metals, if you will, in the periodic table. Now I want to talk a little bit about changes in matter and energy. So you'll see that we'll talk about chemical reactions in numerous times throughout the semester. When you can write, there's one in your book, we just combining carbon and oxygen to form CO2. The atoms have to be balanced. I talk about that in the couple other sections. I'm not going to go into that here. But basically, whatever occurs on the left side of the reaction, which is my reactants, has to also occur on the right side in terms of the individual atoms. Okay, so this is the element carbon. This is the element oxygen. It actually occurs as a diatom, just meaning 2 atoms bound together. This is oxygen gas, and this is carbon dioxide. What I mean is by being balanced is there's 1 carbon over here and 2 oxygen atoms. Over here there's 1 carbon and 2 oxygen atoms. You no longer have oxygen gas on the right side. You now have the carbon dioxide molecule. So this is a case where we have a chemical reaction where we see just the atoms are rearranged, but matter is conserved. Now you'll also learn about radioactive decay. And in this case, you can have a an element that goes through radioactive decay, um, and it releases a particle. And in this case, I'm going to show you a beta particle. The beta particle is um, basically the same structure as an electron, and that is a -1 charge and a 0 up top. So there's no protons or neutrons. It's just an electron. But this actually is a nuclear process, and we'll learn about this in the nuclear section. That is being derived from the nucleus as a result of a proton and neutron breaking down. But just like a chemical reaction, this needs to be balanced. So the top numbers have to actually equal. So 14 plus 0 equals 14, and 7 and -1 equals 6. And this is what determines the elements, so this has to be nitrogen. This is a nuclear process where one element is changing into another. This does not happen in basic chemical reactions, only in nuclear reactions. Chemical reactions involve electrons that surround our nucleus. Chemistry involves with basically exchanging those electrons and sharing those electrons. Nuclear processes involve the nucleus, and that's when you can change one element into another in these nuclear processes. So we'll learn about that in the section of non-renewable energy when we talk about nuclear fission and fusion. One last thing I want to talk about is the electromagnetic spectrum under the section in your book that talks about energy. The electromagnetic spectrum, which is shown here, shows on the left my high energy material waves. So what this is basically energy that moves through space, moves through a vacuum. Okay, so imagine sunlight coming from our star to hit our planet. That is electromagnetic radiation. Okay, electromagnetic radiation includes a whole slew of different types, and many of them you know the names of. Visible light, of course, is what you see. Infrared is what you feel is heat from a fire from the sun. Okay, microwaves is a type of electromagnetic energy that travels through space, comes from stars and other stellar objects, but we can also generate it within an instrument in our kitchen, right? By taking a magnet and electricity and generating microwaves. And we can use that to vibrate molecules. It's actually rotate molecules to heat up a food source. So the only difference between these things, they all travel at the speed of light. When I say the speed of light, that is what you know as 186,000 miles per second. That is the C in Einstein's equation of E equals mc squared. That is the speed of light. These are all considered, if you will, light, electromagnetic radiation. Some people use light to refer to the visible part of the electromagnetic spectrum, which is right here. And these are the wavelengths of the visible spectrum in nanometers. Up here, they're shown also. What we're seeing here as we move in this direction, the wavelength is getting longer, and wavelength is simply measured like this from the peak to the peak. So as the wave gets longer, that means lower energy because the high energy is over here on this side. This also is high frequency. Frequency is the number of oscillations per second. Okay, so basically kind of like the number of waves per second, because a wave is simply one complete oscillation. So this would be a wave. And then another one. So over here, high energy, high frequency. Down here, long wavelength, so low energy, low frequency. And that is the electromagnetic spectrum. And we'll talk about that more because a lot of this will become important in nuclear processes. And then we'll talk about infrared when it comes to global warming and a greenhouse effect. So ultimately now, what I need you to get out of this chapter when you're done reading your PDF files, when you're done reviewing the slides and watching this video, and you go to do your worksheet, you should have a sense of what sustainability means, and that's defined very well in the textbook and in my slides. Be able to distinguish between your capital there, your natural resources, renewable and non-renewable, what it means to degrade that capital, to use up a resource faster than it can be replenished. What are some of the major causes of environmental pollution? Your book talks about this. Population growth is one of the key ones, poverty another one. How we manage our resources, make sure you get comfortable with that. Of course, the scientific process, the scientific method, the structure of matter, basic structure of matter, knowing some of those terms. The changes that matter can undergo, both chemical reactions and these nuclear reactions, and ultimately energy. The changes in energy and things like the laws of thermodynamics that are talked about in your book. And that basically concludes your video.